Good afternoon. It's Friday the 24th. Quite cooler today. Refreshing. Bit breezy earlier and some rain. Now cloudy, clearing, warming up a bit. So last time, and since for some weeks now, day by day, hour by hour, there's been being read a bit of this G.M. Maugin nonlinear electromechanical effects and applications. Now, I acquired this book quite some time ago, actually, and as I begin to read into it, it is about the same time I was collecting some works of Fritz London, and that otherwise, for a long time, I've been looking into what's called the superclassical or superfluidity with respect to Fritz London, and that he's most famous for things to do with things like superconductivity and superfluidity, which are where essentially some of the bounds and linearities of these models vanish, and they happen at extremes or in extremis, like when something is super cooled to near absolute zero, that it might exhibit superconductivity. Or as with regards to how something that is highly compressed might exhibit superfluidity, where basically then these represented in other models where it's basically modeled that some static or dynamical constant is small or low, that it vanishes or that it becomes infinite. And so these are the kinds of things then when I was looking for Maugin, that when I found that he developed these numerical methods and these analytical methods to arrive at what brings us closer to a fuller understanding of the interactions of multiple effects, kind of like if we were to talk about the three-body problem that's so difficult to solve compared to the classical two-body problem, which is completely solved. Or as was mentioned before with respect to Ruffini, Abel, and the quintics, and of the polynomial of order 5, or the quintic equation, to find its roots where they exist, and where that can be expressed in terms of a system of elementary functions or not. That then, with regards to Maugin here, one thing I've been trying to read off piece by piece, where it's not always easy to digest such material all at once or without a considerable amount of thinking or a contextual instruction in the various parts at a time, that as my digestion so followed, it was along the lines of skimming the book and looking at particular sections of prose that kind of spoke to me in terms of relating to things I already kind of well understood, or at least partially understood. That in this manner, I was able to develop, in terms of a knowledge of a thing, a sort of an ontology of a thing. That an ontology is systematic outlay of a classification of things in terms of, in biology, we talk about the genera of flora and fauna and the mineral kingdom and live rust and various myconids and other things that are biological, or as we say that, animate objects. And that as I started thinking about this ontology, then we start talking about like a phylogeny, which is kind of that in terms of the genera, kingdom, species, and dot dot dot. And then underneath a phylogeny, as of an ontology, there's something along the lines of the cladistics, how things are in their lines and how they branch and come back together, the cladistics. And so in terms of an ontology and a phylogeny and a cladistics, these are the sorts of ways we classify large bodies of knowledge, or the corpus. In terms of, here in the biological sense, mostly about our school of what's called the central dogma of molecular biology, which is that as gene machines of a sort, that the science of genomics is as with respect to the genome. This is where the human genome is approximately 10 to the 20-something base pairs of what's called nucleotides in polymers, which are long chemical chains, as of monomers making polymers, that these result in the deoxyribonucleic acid, these nucleotides of base pairs of the four-lettered alphabet, ACTG, or what was that called? I'd have to refresh my memory. But that then these 23 chromosomes, it is, according to the dogma, exist in the nucleus, according to the dogma, that every cell in the human body is so organized as a cell with a nucleus, and as part of the endoplasmic reticulum, it's a cell wall. That within it as well are other what are called organelles and vacuoles, and that there is the mitochondrial DNA, which it would be discussed as later as kind of a Sputnik or partner of the cellular DNA of the eukaryotes after the prokaryotes and such like that. That then genetics and genomics, it has that genomics is the study of the contents of the cell and the chromosomes and the DNA, whereas genetics is the study of the relative traits that are exhibited among people who, according to the theory of inheritance of genetic behavior and the genes themselves, according to this central dogma of molecular biology, that things are determined by their genes, that it so results that this kind of cladistics and phylogeny and ontology are keywords about how we organize massive bodies of knowledge with regards to content of the information of these on the order of 10 to the 20 base pairs of the human chromosome and the genetic material of the human genome. And then as with regards to what's called transcription, how according to these instructions, the program, the code that's in these genome, the various interpreters or transcriptors convert the contents of the DNA according to ribonucleic acid, RNA, into various forms of what are called messenger RNA and tRNA. That what I gathered from this class called Biology 114 and 115 some years ago, where it's just explained that this is the central dogma of molecular biology, and what I gathered from the study of what's called the analysis of the genome and genetics, that then later what's determined is that these transcriptions result that from this linear code of the DNA, there are formed what are called proteins, and the proteome. This is that for the genome, there's the proteome, and that is the corpus of the body of all the collected proteins that are manufactured by the machinery of the cell. And so the proteome and proteomics then it's an entire own field, which is the study according to the processes of cellular replication and DNA replication and the manufacture of proteins and the metabolic pathways of the resulting organs, tissues and organs and cells, which so result in our higher level organization of the human's biological structures, where biological plainly refers to biological reproduction, and the study then of life is as of from when we begin, as before conception through to when we dream at about 5 months into gestation and these kinds of things. And then we were born, and as we begin to gather memories, when we were, various 2 or 3 years old, or when people have their first memories, that in the course of the daily metabolism, in our usual, I forget the words, according to the solar, our circadian rhythms, that it so results that in the course of human development, that humans together, kind of as Carl Sagan pointed out in the previous talk about the discussion of human knowledge, that there's been collected a gathering of books that in the university library you can find a shelf, and on the shelf is about 100 to 150 books. And in these books, from the very beginning to about 9 months later, what you can find is an entire outlay of the determination for the mammalians, and that those share about 90+% of DNA with human beings, or Homo sapiens, or Homo sapiens sapiens, or Homo sapiens sapiens sapiens. That so results that all this is an open book of sorts. And nothing is ever quite totally understood. But it is so well figured out that such things like the blastomeres and what are called the stem cells in the old the multipotent, totipotent, and pluripotent of the stem cells and their differentiation according to environmental factors result that over time there's been developed for this very huge and large body of knowledge a specifics of an ontology, of a phylogeny, of a cladistics, that for our genome and our proteome and what have been determined of the metabolic pathways, then with regards to what are all the environmental factors, kind of the flip side of the central dogma of molecular biology, that cells are determined by their genes, that after a cell divides, that is determined its form as according to its differentiation of what are called the stem cells, the totipotent, multipotent, and pluripotent stem cells, as regards that they result in various actual forms of the body's organs, cells, and that then in terms of the environmental factors, which is whatever is ingested and digested or present, whatever goes out from the contents of the mother's womb, where north and south result the head and tail, all the way to what's for dinner and how's the air. That is so results that a similar kind of approach is made when trying to understand what's going on in the descriptive of these waves. This is where, in terms of our classical periodic motion, as was mentioned, and what results is from the notions of a pendulum, where a spring doesn't quite work because it's always in gravity, but a pendulum, or always kind of biased one side in terms of the limits of the spring's compression, that a pendulum is our usual model of regular periodic motion, and indeed it's used as a test for various large cosmology experiments when planets align in a syzygy or an eclipse, and for some brief moment in the balance of all the potential forces that there's more than one side of a global minimum, that these kinds of things help advise how we get from linear classical solutions with well-defined and simple values up through the higher order and multipole moments, the higher order contributions here of the non-linear, the singular, the infinite, the vanishing. That it so results that then we have a descriptive milieu, that these descriptions are what allow us to frame into plain, simple words what are the complex names of things, their nomenclature, thus that it works out that according to a system of classification, and what results is a system of types, that such a descriptive theory, for example, a descriptive set theory where everything has a model as some form of set, and that all the operations and transformations and relations among them are so modeled. For example, function theory and operator theory and geometry. And that we result for the descriptive that our other models are in terms of those, and they must be necessarily so detailed as they need be to result that there's enough of what we're talking about that it's so clear. So we'd reached back on page 45 where the bookmark was, up to where Maugin had got up past the framing of the quantities to the framing of solutions. And then we get into the messes of solutions, and that according to various initial values and evolutive values, or values that go together in terms of what we talked about, the self parameter or the implicit of the solutions. In terms of the exact, then it's possible to plug in numbers and crunch out numbers. And then near the end of that chapter, as we talked about various methods, including the near field and far field and the coupled amplitude equations, that these are various methods that are applied to all kinds of things that have to do with periodicity, and here to do with the waves and resonances that they've been so put together. Then there's a discussion of the nonlinear vibrations of resonators that we talked about at least a bit, the open and closed resonators, as it were, or bounded and unbounded, that from these settings, then, what I imagine to, after discussing intermodulation, the rate of intermodulation, that is, quote, defined as the ratio of the power developed by the fundamental frequency omega 1 to the power developed by omega equals 2 omega 1 minus omega 2, which you can imagine has been developed as that arithmetic equation in two quantities, one in terms of a linear coefficient relating to the other, that it was as according to what results from various differential equations when other quantities are held so here in time, that was according to a perturbational analysis or simulating the small changes and imagining that then in terms of the dynamical modeling that it results that it can be as around zero, or that things would naturally gravitate or pull away from local minima, or otherwise that it would eventually settle in these things. That he describes a proportion of a ratio, P1 over P omega, should be the power developed by fundamental frequency omega 2. That gets into describing why when we're talking about the discrete particle, vis-a-vis the wave, which is its projection or the intervals as about it, and then that the resonance maybe is ultimately as per where it's continuous, that it's on a continuous substrate, this particle, and it's within a continuous projection, these waves, and then it's as of a continuous time series data, these resonances, that it so works out that brings us up to the appendix after chapter 2, and that I was going to skim forward a bit and scan forward where he discusses more solutions and the hyperbolic equation, where we have the parabola and the hyperbola and other, what results from conic sections, what results from the drawing of the tangent, what results from the inverse and arc cosine and arctangent and the hyperbolic of the parabolic and hyperbolic vis-a-vis the expansions and harmonics. That again, and then he reflects on these some more in terms of the near field and the far field and the sinusoidal, and in terms of the steepening or determining what when something changes with respect to whether it's linear or not, when it approaches linearity, or how the components would add up back together, that in terms of the original linear equation that there's a contribution. And forced excitations, the Galerkin method. The Galerkin method is frequently employed to solve nonlinear wave propagation problems in finite regions, in our case resonators. Reading off from the appendix of chapter 2.5. This method essentially consists in assuming the spatial variations, such as the linear mode shapes, using the orthogonality properties of the mode shapes, and obtaining nonlinear coupled second-order differential equations which describe the temporal behavior. Then the latter equations are solved by using a perturbation technique such as the one on multiple scales, recalled above in paragraph 3, or another method such as the so-called method of averaging. Accuracy of the method can be evaluated thus. Galerkin method. So again, skimming forward is to the solitary waves, the Korteweg-de Vries equation, which is in the differential equations as of differences according to time and one of the position parameters. Then as to very notions of trajectories, the solitons are introduced. Solitons, like the phonon, like the photon, like the instanton. Soliton is basically a linear impulse. Solitons are multiple solitary wave solutions which behave like particles in the course of interactions, collisions. The inverse scattering method is an essential tool for the construction and study of these solitons. For these developments, we refer the reader to Zakharov, inverse scattering method, Roseau, vibrations des systèmes mécaniques. For an involved example, in elastic ferroelectric crystals, see J. Puget and G. Maugin, J. Puget and G. Maugin, and J. Puget and G. Maugin. Solitons and electroacoustic interactions in ferroelectric crystals. Now myself, looking back, one of the only things I'm really kind of unfamiliar with is this non-dimensionality, as was mentioned in the acoustic Christoffel tensor. But when it comes to solitons and phonons, the acoustic, and instantons, which are in point particles from fundamental physics, and photons, which are light particles, that these are all kind of related in a hierarchy even of sorts, that the soliton is basically the mathematical bit, others mostly with the physical interpretation. That then there's a reference again to the coupled amplitude equations, which is when constructive or destructive interference is basically assumed, I imagine, that the amplitudes happen to be so bound or proportional and result. And when there's the addition of kinetics or vibrations, we usually think of kinetics as in terms of an impulse as to throw something to result that it gains velocity, then vibration is the gaining of kinetic energy in terms of a back and forth notion, as about a resonating, as you might imagine, where the energy is contained in the kinetics and is dissipated and attenuated as transmitting to, in the continuous sense, a sound, like a tuning fork, but in a discrete sense into these phonons, or what result any particle model of a continuous quantity. The kinetics that don't involve displacement. That reading on, he mentions the frequency dependence of the dielectric tensor, that kind of ends the appendix, that we reach chapter 3, Rayleigh surface waves. Rayleigh, we think of Rayleigh and Rayleigh genes, and with respect to the ultraviolet catastrophe and some of the first notions of the particle and the discrete, and what happens when there must be a discrete amount of energy, and that it's still kind of paradoxical, and we can point to Hooke's law for that. Hooke's law is about a spring, that we cannot add all these particles together if they're continuous, because it would result in infinite quantity. But these particles' energy must be some sort of discrete value that it can't really be continuous in its variation, because then that would add up somehow to an irrational or continuous quantity. Now, to leave it in the milieu where these particles can be added up and they can be treated like a gas of particles, according to like Boyle's gas law and this kind of thing, this is where there are methods that are tractable for particles and methods that's tractable for waves, as we're discussing here, and then that we determine these in terms of things like Liénard-Wiechert and electrons in their holes, the negative and positive of charge in the voltage differential or the potential of an open circuit, and that is so fulfilled when it would be broken as by a closed circuit or a running circuit, that the Rayleigh surface waves chapter begins like so. 3.0 Introduction. Surface waves are particularly interesting in so-called SAW devices. SAW equals surface acoustic wave. Used in signal processes, they allow the conception of delay lines and harmonic generators. The paragon of surface waves is the Rayleigh wave. R-A-Y-L-E-I-G-H, Rayleigh. Similar to Raleigh, but Rayleigh. In linear isotropic elasticity, which is recalled in Appendix 3.1. Its elastic displacement, in reason of the very large material symmetry, is parallel to the sagittal plane, or sagittal, spanned by the direction of propagation and the unit normal to the limiting surface. The sagittal plane. This is no longer the case for the media of interest in this chapter, which are crystals. That is where crystals vibrate altogether. Therefore, the elastic displacement of the considered surface waves has three components. The nonlinear case is studied using a straightforward expansion method, near-field solution, and the multiple scale method, far-field solution. This is where we discussed earlier that there is a near-field solution and a far-field solution, and there are others, and it's to be figured out what is this abstraction, which is this generic, which is just genera, to identify what properties entail that you can call something, as you might call an exact solution, a near-field or far-field solution. The electroelastic couplings of the linear piezoelectric type are taken into account only insofar as they allow to excite elastic waves of the surface type in the crystal via the so-called direct piezoelectric effect in a transducer of the interdigitated type, and they allow the detection of elastic surface waves via the so-called inverse piezoelectric effect in a transducer receiver of the same type, since the substrate, e.g. quartz, is weakly piezoelectric. So what this is reflecting kind of is in a sense that when we talk about the core and the skin effects, that there's the notion that there's various eddies and currents and the velocity that flows differently on the surface and in skin, or on the core in the center, or through the center. And it's similarly when we have open and closed resonators, like a closed resonator like the Earth, which is an oblong shape that's approximately spherical and 25,000 miles across. In terms of waves of earthquakes and their various forms and what they are in terms of, here we're talking about a crystal substrate and whether it's actually a lattice of the crystals, or for example where they have that they're the symmetries of their parallel and facing faces and their cosites and such aspects of a lattice make for that. Essentially, a lattice is an empty framework with orthogonal corners, and a crystal is the bodies inside that. Kind of like a sphere is an outwardly circular shape, equidistant in its radius from a center or origin. The ball is the sphere that is full. So these crystals basically are the space filling the lattice, and then in the sense that they have material properties or not is basically whether we talk about those waves carrying through the various connections or the various spaces. And here we're talking about over the areas of the surfaces of these objects, which you can basically here abstract as a cube. That is like a cube of quartz, or insofar as quartz has a cubic structure in its crystallography. According to the acoustic Christoffel tensor, after Christoffel is most famous for an entire classification of crystals according to various solids in the pyramidal and cubic and rhombic that result all sorts manners of materials like diamonds and cubes and these sorts of things. So after the piezoelectric and inverse piezoelectric effect, where the piezoelectric is that the induction of an electrical current causes vibration, or that vibration causes the induction of an electrical current. The effect, that an effect is basically a transition between one form of energy and another. Whenever you hear effect, like the Seebeck effect or the Peltier effect or any other effect that is usually defined in terms of dynamics, what the effect is that it changes one thing to another. The generation of harmonics and the phenomenon of anisochronyism, not isochronism, are exhibited for elastic surface waves. In contrast to the case of bulk waves, anisochronism here depends on the distance traveled by the wave, which can be many wavelengths. The phenomenon of nonlinear coupling between pre-deformation and crystal for surface waves is recalled in Appendix 3.A.2. So here he just defines surface waves and the Rayleigh wave. And he hasn't quite defined the Rayleigh wave yet, except that it's surface waves. So then 3.1's title is Excitation and Detection by Means of Interdigitated Transducers. In our sampling and our measurement and our observation of things, we need to have something that's called a detector or collector. And so this might be a phosphorescent screen that would convert an electron to a photon, or something like a bell that when you strike it, it rings, or anything that does that here. Here, the particular thing that they're using to describe this seems as if like it's interdigitated, it has fingers, and then it's kind of like a comb, so that then when various aspects or fringes or edges or ripples of the wave reach the comb, that it's describing an interdigitated transducer, and as regards to that in terms of this piezoelectric wave, that when it reaches this measurement, aka sampling, aka observation device, a detector, where those may be equated as to the same or different terms depending on abstraction and configuration of experiment and energy of experiment, that the direct piezoelectric effect is used for the excitation of elastic surface waves in a substrate made of a weakly piezoelectric material such as quartz. The transducer is of the interdigitated or comb-like type with a spatial periodicity of digits equal to half the desired wavelength. The spatial periodicity of digits equal to half the desired wavelength. Now, the wavelength is basically the full period, and then the half period, it reflects that because it's restitutive or reciprocating, that as something goes back and forth, to sample something, you need twice as dense as the thing to be sampled to get a reconstruction of the signal. For this, what you'd like to know is something about what's called Nyquist theorem, N-Y-Q-U-I-S-T, Nyquist theorem, and Claude Shannon, that Shannon and Nyquist, for whom it's usually named Nyquist, that for B over 2A, or with regards to the period, that 1/2 the period, or twice the frequency, is necessary to sample enough samples to be able to reconstruct the signal, otherwise there'd be signal loss. So this notion of Nyquist sampling theorem is that you have to sample something twice as much as it makes waves, or its extent. Thus, that in this manner, you don't lose it halfway through on either side. And this way you can maintain for a sampling line of a sorts, as something crosses a surface, that you have enough points of its continuum to draw a pointillist drawing of it and a result that looks about the same as a continuous image, and not have a half-tone dithering or something to do with along the lines of signal loss. So that's what he's describing, the reason why that the transducer has a spatial periodicity of digits, its comb fingers, equal to half the desired wavelength. A is the relative width of the electrodes. According to the direct piezoelectric effect in the linear theory, we have at frequency omega, rho sub r omega squared u sub j plus c ijkl u k comma la equals negative e sub lij phi l comma I. Recalling that those are the components that went into our description of our linear wave equation. And this equation has to be solved for the potential distribution developed by the transducer. So here he describes that in terms of the way these things react, that they build a potential. There's the charge that builds the electricity. Now, before electricity was named for the phenomenon of moving charge in electrical circuits, electricity still had this intent and this meaning of the potential before the lightning strikes or something like that. That here he's describing then for the potential distribution, that he's making the realistic statement that whatever it is we end up solving for it classically by our approximation in our linear methods, and these other things hold neatly so in our monomode process, so boxed, that then there's this outer circle of these things that really reflects the potential distribution, and that otherwise it reflects that electricity in its fluid model and all such manners of kinetic energy and electrical energy in this always have the potential energy as what represents here voltage difference, or why then that results that according to Kirchhoff law and Ohm's law, that when it can be measured, that it's a simple function of the voltage difference over the amperage, the resistance, what results a value that the detector can display or have sampled its measurement after observation. This first step, therefore, is to compute phi for the given transducer, and he's written a diagram scheme of a surface acoustic wave delay line. That a delay line allows something like when you receive a signal to hold it for a second and then broadcast it, or when you receive a signal to reinforce it and provide it with amplitude or gain. Although there are many machines or devices that can be so implemented this way. So now we've been reading at this for a while, and we've talked about Rayleigh surface waves, and I just want to find some other surface, as it were, definitions as when we're talking about the contributions. Here that the Rayleigh wave emitted corresponds to the contribution of the pole K naught, K sub 0. Its amplitude is obtained by using the theorem of residues. That and then in chapter C describes detection, and then nonlinear propagation. So all that was linear propagation, and then into nonlinear propagation, where those are the nonlinear contributions until such point as we reach the superclassical or the superfluid in our fluid models, that it's all nonlinear or higher order or multipole or asymptotic or singular, that he introduces many of the same sorts of methods of solutions in the near field and far field after Poincaré's. And in the appendix then, he discusses the classical Rayleigh wave and its admissible solutions, mentions the Poisson ratio, the celebrated Rayleigh equation, of which only the positive roots smaller than 1 are admissible. This, reading back to an earlier discussion where we talked about the additive and multiplicative identities and the value of something between 0 and 1, resulting that its infinite power is between 0 and 1. And the Poisson ratio is in terms of gamma over 2, quantity gamma plus mu. That here's an example of something in terms of like the sampling frequency, or again, one of these perfect ratios with regards to putting it in the box, having it in the box, squaring it in the box, making a quadrature, and having it out. Has that these are reasons why they're so celebrated, because they end up crunching numbers with simple arithmetic. That the above studied Rayleigh waves in a linear isotropic solid have an elastic displacement polarized parallel to the sagittal plane, sagittal or sagittal. Therefore, the question arises of the existence of the surface waves carrying an elastic displacement polarized in a direction orthogonal to the sagittal plane, so-called SH waves. SH equals shear horizontal, according to the seismological jargon. Here referring back to our mention of the Earth as a resonator, that's seismology is the study of earthquakes. Such waves, called love waves after their discovery by the elastician A.E.H. Love, are shown to exist for linear isotropic bodies whenever a layer of softer elastic material is superimposed on the semi-infinite substrate. Here he describes that according to the method of propagation, in basically what's softer is only what's defined as that the speed of propagation will be faster so that it would dissipate out more, or that its power so carried, according to what we were talking about earlier about this wave propagation and Rayleigh and Hooke's law, and the dissipation of the attenuation of waves as there is so entropy has that there's a boundary between this inner layer and outer layer, and he's establishing why there are these particular shear horizontal waves vis-a-vis the surface acoustic wave. One says that the superimposed layer is a slow layer. The reader has referred to the already cited book of Achenbach's, also the K.F. Graf, Wave Motion Elastic Solids, Ohio State University Press, Columbus, Ohio, 1975, for a study of love waves. SH waves of the bulk and surface types are extremely important in seismology. They correspond to a so-called anti-plane motion. In linear piezoelectricities, SH surface waves can be shown to exist on the condition that x cubed in this figure, x cubed being this here, x cubed, in figure 3.1a being axis of symmetry of order 6, e.g. in cadmium sulfate, CDS, oriented in the correct manner. This is where cadmium sulfate is among these materials with these given properties, according to its usual crystalline structure as a pure metal, that it has these properties. Then they are called Bluestein-Guliev waves after their simultaneous discovery by J.L. Bluestein, 1968 in the USA, and Guliev, 1969 in the USSR. These Bluestein-Guliev surface waves penetrate very deeply in the substrate, depths of penetration of the order of 4 to 50 angstroms. I believe that's what he's reading as lambdas there. But correlatively, their phase velocity is extremely close to the bulk transverse wave speed. Those are probably bigger than angstroms. Their phase velocity is extremely close to the bulk transverse wave speed, so that they are very close to degenerating into phase shear waves. This is where the degenerating is where something falls apart and essentially collapses. It kind of like when you shoot a fountain in the air, it essentially degenerates and falling at some point back in time upon itself, and that's an example of something that's degenerating. That these Bluestein-Guliev waves degenerate into face shear waves. We were talking before about shear horizontal. These are face shear waves, where the crystals have faces, which are the things that connect their corners. Or in terms of they having a graph as their structure, that the edges and vertices define that the areas contained by the edges, as it so exists in a geometry, are the faces of the crystals. Their existence is due uniquely to the fact that electrical conditions perturbate the usual mechanical boundary conditions. This is the vibration of the electricity, or the electricity of the vibration, and as to why such charge, such energy, such potential results, what results would similarly emanate radio wave emission, and that otherwise there's stuff going on with that. Their existence is due uniquely for these and other types of SH surface waves in inhomogeneous elastic media, ferroelectric crystals, and ferromagnetic crystals. The reader is referred to G. Maugin, surface elastic waves with transverse horizontal polarization. Applied Mechanics, Volume 23, editor J.W. Hutchinson, Academic Press, New York, 1983, pages 373 through 434. So, in an anisotropic crystalline, for propagation at any angle from crystallographic axes, the confinement of the elastic displacement of surface waves to the sagittal plane is no longer obtained, and the corresponding surface elastic waves with three coupled Cartesian components, one of which orthogonal to P_S, sagittal plane, may be called a generalized Rayleigh wave. Generalized usually means that instead of other things held constant, that without loss of generality, the other things are not held constant. Generalized. From the above treatment, however, we note that the solution will then be a linear combination of three elementary modes instead of two. CF equation 8.14. Recall that the modes were as of the nonlinear modes, where those two second and third order contributions were reduced to first and second order contributions, where the linear overall contribution has order rank 0 because it's assigned the value 1, where it was so defined that it resulted that the linear contribution was a unity and that the other things were in terms of it. The influence of a pre-strain on such a solution is examined below. It discusses the stress and the strain tensors, and then we talked about deformation. And so this pre-strain and pre-deformation are what happen kind of as the impulse begins to establish what is the result of an elastic collision or an impulse, that it arrives at that as through infinite degrees of coming together. All right, then, well, that's enough reading, I suppose, for today. So we left off at page 145, and we're looking at page 142, and the time has rolled on, and it's going on about the day. We talked a little bit about ontology, a little bit about the central dogma of molecular biology. I wonder what this is here. Let's see. This is dynamic light scattering. So we've been looking at the dynamic light scattering and the multiple beam interferometry of surfaces of films together, and this is with applications to chemistry, biology, and physics. So dynamic light scattering takes us back to the discussion of the scattering techniques. Now, scattering is how we model the dissipation of quantum particles, as per somebody like Richard Feynman, and as was mentioned, the discovery of such methods for the acoustic, that scattering kind of reflects that these discrete fundamental particles yet still propagate in terms of as of every direction at once. That, for example, it's a perfect circle that they get out of instead of that they are some spiky box of things. And so scattering are what results, for example, in the diagrams when we have, for example, if there was an atom or smallest length like the Planck length, then you couldn't really have any right angles because the distance between two units of those at right angles would be an irrational in the square root of 2, as anyone's familiar with who's ever proved to themselves that there exists an irrational number, at least one of which being the square root of 2, which has no integer ratio that represents it. So scattering then has a complementary theory of what's called tunneling. There's that in the quantum mechanics dynamics that basically the Feynman diagrams add up for the path integral to make up stuff for what's called scattering. And then how they come back together is also part of the path integral, and it makes up what's called tunneling. And so both of these together are kind of these things that then in terms of dynamic light scattering, that we talk about the features of light-like quantities, which are different than space-like and time-like quantities. And in that their paths, or as they follow the geodesy, or rather as they flow in their flux, that light is basically always fleeting. Light is always motion. There is shadow and there is light. There is the intromissive and extromissive theories of light, and today we almost entirely deal with what's called an intromissive theory of vision of light, that light is extromissive. And not that our eyes look out to something and broadcast a ray and it comes back to our eyes as like a laser ranging or something like that. The intromissive and extromissive theories of vision. But that light is always fleeting, and in fact, light is always gone. The idea here that light speed is constant and infinite, in the sense that light speed is measured to be 3.0 times 10 to the 8th or so meters per second. If I don't get my units wrong, it's 3.10 to the 6th or 8th, I forget. It's 2.98 to the 10 meters per second, light's measured speed in a vacuum. But insofar as that regards in the theory, then it kind of results that light speed is always as a flowing away, like the breaking radiation or bremsstrahlung, that this dynamic light scattering is building up what's going on in this field where the electromechanical is not light-like. It's all classical. It's all less than C. It's all kinetic, and according to the classical and potential theories of waves. While it's still so that in a perfect superconductor, electron holes rotate at C. Or nearly so. They are essentially attaining to the velocity that's the maximum in that space with regards to any of these distortions according to relativistic dynamics and what's called space contraction, as a combination of time dilation and length contraction, which are effects on space-time that result when you provide a given distance of an area with the Lorentzian derivations of what's called special relativity, that light speeds is a constant, and that according to E equals mc squared, that the energy as you reach that speed would be infinite. And so we would talk about that a little bit later. And as to why otherwise, that this theory of the scattering of light has to do with that light is always scattering, light is always fleeting, light is flux, the flow of things. And in that way, it's as of a fluid model again, and a superfluid model. Light has a superfluid model. And that this is a way we can address it at once, as having both of the same kind of mechanism while still being very different substances and having very different qualities. So that said, that was what's there, and I'll set that up here like so. And there's time, differential topology and quantum field theory. This gets into some similar notions, I'd imagine. This is mostly mathematical. This is in terms of making models that are algebras, that have then physical interpretations by making models of those. But it does get into instantons and monopoles. It used to be a theory that there's no magnetic monopole, and an instanton is a difficult thing to compute with, so leave it alone. This is some of the idea to get up Yang-Mills theories to talk about Yukawa potentials. The Yukawa potential is basically the bread and butter things in terms of Yang-Mills theories, which is basically the premier theory up above Kaluza-Klein, which is 3 dimensions for time, 3 dimensions for space, 1 for time, and 1 dimension for projection, or working dimension. So that's multiple beam interferometry, and we'll just leave that up there. It'll fit on the shelf. And then we'll get back to this nonlinear electromechanical effects and applications a little bit more since we've talked about the surface acoustic wave, Rayleigh waves, and the shear horizontal waves, love waves, and the Bluestein-Guriev waves, and their matters of fact. All right then, good afternoon. Happy trails.